Okay, welcome back everyone to the world of harmonic measure. Today I'm going to review some basic results about harmonic measure, then discuss how one calculates it approximately in certain cases, and explain how harmonic measure controls not just harmonic functions but analytic functions. And this is one of its main applications. So this is another example of a conformal invariant. So I'm often implicitly assuming or saying things are conformal invariants, or maybe not even stating that, but let me emphasize that that's the case here. So let me remind you again what the definition is of harmonic measure. So the setting is, at least initially, we have a domain omega, which is, say, finitely connected and contained in the plane. And the picture you should have in mind is you might just picture a Jordan domain, but maybe allow it to have a couple of holes. That's omega. And then we have a point in omega and a subset of the boundary. Let me make it, and usually we'll think of this subset will usually be something like just an arc, as I've drawn it here. And we want to know how much the values of a continuous function on the boundary of omega, how much the values of that function on A influence its harmonic extension to the point Z. So in particular, we have a solution to the Dirichlet problem at hand. In this case, we proved that last time using Schwarz's alternating method. And of course, solving the Dirichlet problem is a conformally natural procedure. So we can take continuous functions and extend them to harmonic functions on the interior of omega. So the boundary values go to something harmonic. But we can also do this for piecewise continuous functions. And so what we do to determine the influence of A on the point Z is we create a harmonic boundary values, which are 1 on A, and which are 0 everywhere else on the boundary of omega. And then we see what that function comes out to be at the point Z. So omega Z omega capital little omega, the harmonic measure of A as seen from Z through big omega, is nothing more than the harmonic extension of the indicator function of A, which is 1 on A and 0 on the rest of the boundary of omega. So it's really just sort of a psychological thing that we think of fixing Z and varying A. And then this becomes a measure on the boundary. And of course, the harmonic extension of the whole boundary would just be the harmonic extension of the function 1, which would be the constant 1. So indeed, this behaves like a probability measure as we vary the set A. Okay, so this is called the harmonic measure of A. As seen from Z, and one should keep the domain omega in mind as well, which is why the notation records all three of those quantities. Now, there's two ways you could extend this definition, which would be very natural. One is you could replace A by just a function on the boundary. And so we could also set, this is an extension or a variant. We could also write omega Z, omega, and then just capital phi, and let this be phi of Z, the harmonic extension of the boundary values capital Phi. This notation is not in common usage because it clashes with our psychological idea that we're measuring the sizes of sets. But if we were to introduce this notation, which will be useful, then this would be the same thing as we could just replace A with the indicator function of A. And we get the same concept of measure. The other kind of extension that's useful is, well, here's something that's obvious but important, that there's a certain monotonicity to omega. And when you want to do a computation of harmonic measure, often you're happy to get upper and lower bounds. So when does the harmonic measure get bigger? Well, this increases with A. If A gets bigger, then the harmonic measure gets bigger. And that's obvious because if you make A bigger, then say you enlarge this to a bigger set A prime, then the indicator function of A prime is greater than or equal to the indicator function of A. And that implies the corresponding harmonic extensions satisfy this inequality. And after all, omega of Z omega A is just the value of the harmonic extension at a particular point. So an important property of harmonic extensions is that they are monotone in the boundary data. As the boundary data goes up, the harmonic extension goes up. So if we make the boundary data bigger, then of course the harmonic measure goes up at the point Z. In other words, a bigger set has more influence. Okay, now here's something a little bit radical. We could also let A go into the region omega. That looks a little dangerous. What are you talking about? Well, we extend the definition by saying that if A happens to enter the region omega, we just make the region smaller. And so we can also define omega Z, omega A in the case where A might go inside of the region. What this really means is omega of Z, and then you delete A from the region, and then you take the measure of A intersect the boundary of this new region. Okay, so we could push A inside the region, and then we would be looking at a function that's equal to 1 here, rather than a function that's equal to 1 here. And now the harmonic extension of the indicator function of A is less than or equal to 1 inside of this whole region, because it lies between 0 and 1. So it lies below 1 on this boundary. So if we look at the harmonic function that's 1 here, it again lies above the harmonic function that's 1 just on A. So this is true. This increasing property is also true even if A goes into the region omega. And it's frequently useful when bounding harmonic measure to just have this flexible way of thinking. So the bigger A gets, the more Z feels its impact when we solve the Dirichlet problem. Okay, now here's an interesting question. What if instead of making A bigger, we make omega bigger? So we add some stuff to omega and create a larger region omega prime. Does the harmonic measure go up or down?
I think it should go down because there's more that it could hit.
Okay. How many, raise your hand using reactions if you think it should go down. Everybody, this is not a binding vote. This is just a straw vote. Okay, so I see 5 votes for down. Okay, now put your hands down and raise your hand if you think it should go up. This is how all mathematical issues should be settled, really. It's by a fair democratic process. I don't see any hands making it go up. Okay, well, surprise, surprise, it actually goes up when omega gets bigger. So try to grok this. This is kind of omega. It also increases with omega. Okay, so let's get very clear on why this is true. There are a couple ways to think about it. And let me simplify my picture by just making it a Jordan domain. And A is an arc on the boundary. So why does the harmonic measure of A, why does A look bigger the bigger we make omega? So here was our old omega, and we solved for, we have a solution phi, which is harmonic on omega, and then we have a solution phi prime to our boundary value problem on the bigger region omega prime. Okay, so phi prime is equal to 0 out here. Phi is, this is the old boundary of omega here, so phi is equal to 0 here. And phi prime is living out here, and they both are equal to 1 on A itself, and they're both equal to 0 on the common boundary of omega and omega prime. So the place where we can compare these two harmonic functions is along this line here. Let me call this line A. Now phi is equal to 0 on A. But what about phi prime? Well, phi prime is harmonic in this whole region. So it's between 0 and 1 within this whole region, but typically it will be bigger than 0 along this arc A. It will already be starting to feel some of the influence of that A. So phi prime is greater than or equal to 0 on A. Sorry, I'm writing this in backward English, 0 on A. So in any case, phi prime is bigger than phi on the boundary of omega. And so phi prime of z is bigger than phi. And that says that the harmonic measure goes up. So remarkably, the harmonic measure goes up when you make A bigger and when you make the whole domain bigger. Okay, now let's try to make this intuitively obvious. So if the domain were a Jordan domain, then by the Riemann mapping theorem, we would have a hyperbolic metric on this region. And how would we construct the measure of A? Let's do it on omega first. What we would do is we would take a hyperbolic geodesic, and we'd choose its angle at random, a hyperbolic ray based at C, and we'd see the probability that it hits A. And sometimes it would go, sorry, I shouldn't have called this A. Let's call this B. Sometimes it goes over and hits this arc B. And then it has to be 0. But what happens is that, at least in principle, when we make the region bigger, when it hits B, it might just hit it with sort of a glancing blow. It might come over like this and hit B, go a little bit into omega, come back and come over and hit A. So when this barrier B is in place, it's harder to see A. And when there's more room, there's more opportunities for arcs to come back and hit A. So in other words, one way you can think of this is that the part of the arc that's 0 is pulling the harmonic measure down. And what we've done when we make the region larger is we've pulled that region farther away so that this 0 has less influence than this 0 set. In fact, it's exactly, if you were to just reverse the roles of A and B, A and its complement on the boundary, in fact, it follows from this statement where we allow A to go into the region that adding more stuff to the region makes the harmonic measure go up. Okay, so it's very important to have this intuition and to have it going the right way for you. Okay, so I hope that makes sense. Another example to make it seem very obvious is if we were to take a square, let's say, sorry, a rectangle like this, take this to be our domain omega. This bottom arc is A, and we pick a point Z here. Now, what's the harmonic measure of A as seen from Z? Well, it certainly is at least a quarter. It's quite big, and the smaller this rectangle gets, the closer it gets to 1. Sorry, that's not what I wanted to say. Sorry, I'm saying this the wrong way. Pardon me. Okay, let me set aside this example. We will later see an example where the monotonicity becomes very clear. But I just wanted to explain from general principles why it always holds. Okay, now what is the point of harmonic measure? The first point is that you can use it to control the values of harmonic functions. You can use it to bound them from above. Everything is set up for upper bounds. Of course, it also yields lower bounds. So we have this monotonicity principle. Just want to record that. Omega Z A, omega increases with A and omega. And the next thing is what I'm going to call majorization. And for this, I like to think of it in terms of having partitioned the boundary of omega into 2 pieces. So we have a piece A, and then we have the rest of the boundary, which I'll call B. Of course, the harmonic measure of the 2 of them put together sums up to 1. So let's set the harmonic measure at Z omega of A be equal to P, and then the harmonic measure of the rest will be equal to 1 minus P. And of course, P is between 0 and 1. And now suppose we have a function, boundary data, capital Phi, and if phi is less than or equal to m on A, and phi is less than or equal to little m on B, then what do you think we can say about the value of phi at Z? Well, this implies that the value of the harmonic extension at Z is less than or equal to some linear combination of big M and little m. And what are the relative weights? They're just the harmonic measures. So it's bounded by P times M plus 1 minus P times little m. So you see, normally, if M is big and little m is small, the most you could say using the naive maximum principle is that the value of phi is less than or equal to m. But you should also take into account the fact that there's a large piece of the boundary where the maximum is less than little m. And the harmonic measure tells you you're allowed to use that bound. You can, the correct bound is a linear combination of the 2 given bounds weighted by the harmonic measure. So that's one of the useful features of harmonic measure, is that it lets you, instead of just looking at the maximum of the boundary values, it lets you weight the maximum according to its value over different regions. Now, why, for example, is this true? It's very simple. We can sum this statement up by saying phi is less than or equal to m times the indicator function of A plus little m times the indicator function of B. And so what is phi of Z? It's omega Z omega capital Phi. In my monotonicity, that's less than or equal to omega Z omega m indicator function of A plus little m indicator function of b. But the harmonic extension is linear, so this is less than or equal to big M times the harmonic measure of A plus little m times the harmonic measure of B. And these are P and 1 minus P respectively. So that's the principle of majorization as applied to harmonic functions. However, I think where harmonic measure really shines is not in the control of harmonic functions, but in the control of analytic functions. And the control for analytic functions might seem a little surprising at first, because instead of obtaining this kind of additive control, we're going to obtain a multiplicative control. So let me keep my setting the same here, but now I'm going to majorize an analytic function rather than a harmonic one. So the theorem is that f omega c be a bounded analytic function with the absolute value of f less than or equal to m on A, and the absolute value of f less than or equal to little m on B. So I'm implicitly assuming that f has boundary values on this arc and on the complementary arc. Then, what can we say about the absolute value of f at z? Well, remarkably, it's less than or equal to m to the p times little m to the 1 minus p. So we get a multiplicative bound on f. Notice, for example, that if A and B had equal harmonic measure, what would this product be?
Geometric mean of mm.
Exactly. So that would be the square root of this product, which would be the geometric mean of the big and small bounds. And in general, this is what's called a weighted geometric mean. It's a product of numbers to certain exponents that sum to 1. So what we get is a bound on the absolute value of f, which is the weighted geometric mean of its sizes on these two arcs A and B. Now look how much stronger this statement is than the statement we had for harmonic functions. So for harmonic functions, we just got an upper bound. By the way, we don't even have a lower bound on the function in this case. But here, we're bounding the absolute value of f, which is of course, positive. And now let's look at what happens as the bound little m goes to 0 while keeping big M fixed. If we keep big M fixed, but little m goes to 0, then this whole quantity goes to 0. In particular, if you knew that f was 0 on this arc, then it would be forced to be 0 in the whole region. And that's not too surprising, because we know that an analytic function that vanishes on the boundary has to vanish everywhere. And this is somehow a quantitative boosting of that qualitative statement. So if f is very small on B, then in fact it has to be very small through most of the region, unless it's enormous on A to compensate. Okay, so this is really I think one of the prime examples of the use of harmonic measure. And there are many theorems in classical complex analysis about controlling the size of an analytic function that become very simple and conceptual once they're recast in terms of harmonic measure. Now, I haven't proved this theorem for you. What's the proof? The proof is we consider the function phi of z, which is the log of the absolute value of f of z, and we apply the previous bound to this harmonic function. To get that that phi of z is less than or equal to p log capital M plus 1 minus p log little m. Okay, now here's your chance to play the role of grader instead of homework writer. How many points does this proof get? It's less than 10. What's wrong with this as an answer?
I suppose, like, how do we know that log absolute value of f of z is harmonic?
Yeah, right. So this would be good if we knew this function was harmonic. And indeed, it is harmonic because we can write it as the real part of the log of f of z, which is analytic, except if f happens to vanish. But what happens when f vanishes? This function tends to minus infinity because the log of 0 is minus infinity. So as we discussed earlier, this is not a harmonic function. This is a subharmonic function. However, the theorem that we gave last time that we're applying here gives a bound for harmonic functions, and subharmonic functions always lie below the harmonic function with the same boundary values. So since we're giving an upper bound here, it also gives an upper bound for this subharmonic function, and therefore the proof is correct. Now, it might make people feel uneasy to say I'm going to start applying the maximum principle to functions which aren't even defined at some points or where they're minus infinity. Just to give you a little more confidence, when you have a function on a domain omega, and let me just draw it sort of conceptually in cross section. So we have the boundary of omega here and here. And you have this subharmonic function, which happens to have these go to minus infinity at certain points. One thing you can do is you can take the boundary values of this function and you can take their harmonic extension. And now I claim that this function with these bad singularities lies below the function, the harmonic extension of the given boundary values. And the reason is that when you go to one of these singularities, the function is going to minus infinity. So it definitely is below the harmonic extension, which has a finite value there. So you could just excise from omega a small ball around this point and another ball around this point. And now the white curve is harmonic on the complementary region, as is the red curve, and the white curve lies below the red curve on the boundary of the region with these two holes introduced. And then by the usual maximum principle, the values of the white curve are majorized by the values of the red curve. Okay, so either way, this is something one should worry about and think about, but it works just fine. Any bound, upper bound that works for harmonic functions gives an upper bound for subharmonic functions that have the same boundary values. Okay, so that's the majorization principle for analytic functions. And now as an application, where we're going to do it for once, a multiply connected domain, I want to prove Hadamard's three circles theorem. So Hadamard's theorem is traditionally phrased in the following way. We have a function f. Let's say it's mapping at least some annulus with inner radii a and b to the complex plane. So it's defined at least between two circles, the circle of radius a and the circle of radius b. Often people study entire functions using Hadamard's theorem, but we only need it to be defined in this region. And then one of the interesting quantities to study is m of r, which is the sup over the absolute value of c is equal to r of the absolute value of f of c. So we're interested in bounding on some radius r the absolute value of f. And this is a quite common topic of study in entire functions. You have an entire function and you want to understand what its maximum value is on the circle of radius r. By the maximum principle, this function is increasing. How fast does it increase? How does it behave as r varies? By the way, when the function is on an annulus, it doesn't have to be increasing. The function might be 1 over z, in which case m of r is a decreasing function of r. So the theorem is that log m of r is a convex function of log r. Now that's a kind of funny looking statement. What does that mean? We have to change everything to logarithmic coordinates. But what it means in practice is the following. So for example, if r is equal to the geometric mean of a and b, the inner and outer boundaries of the annulus, then it says that the value m of r is less than or equal to the geometric mean of the value of at the inner boundary and the value of the outer boundary. B. So again, by the maximum principle, you would only have that this function is that its values between, so if you just knew the maximum principle, you would be looking at the values of log m of r, and you know the values at two endpoints, and then the maximum principle would say the graph of the function lies below the maximum of those two values. But the Hadamard's theorem says that at least if we're looking at this as a function of log r, it lies below the straight line joining those two functions. That's why this inequality is stronger when the function f is big on this boundary but small on this boundary. Both the large and small bounds play a role in controlling the value of f. And in general, the function in these logarithmic coordinates looks something like this. It turns out to be convex. Okay, so Hadamard's theorem is perfect for applying this theorem. We'll take omega to be this annulus here. Now, what should we take to be our arcs A and B?
The inner and outer boundary?
Yeah, sure. That's where we have control. We're gonna suppose we know what the value is on A and we know what the value is on B, and then we're going to try to control f in between. Now, of course, what we wanted, that will show convexity between these 2 points. Convexity in general, you'll have to take an arbitrary 2 points, but it will follow if we establish convexity for A and B, then the convexity will follow in general. So here's so for the proof, first, it's enough to show that when the absolute value of z is equal to r, and now what we're going to do is we're going to write r as a weighted geometric mean of A and B. So write it as A to the p times b to the 1 minus b, that m of r is less than or equal to m of A to the p times m of b to the 1 over p. That's just a translation of this convexity statement into a statement about m without taking logarithms. Okay, so how do we get this? We let A be the circle of radius r of A, and we let B be the circle of radius B. And now what we need to know is what's the harmonic measure at our point Z, which is on this circle here, what's the harmonic measure of the inner boundary of the annulus? What's the harmonic measure of the outer boundary? Well, this is something we computed already. So a good way to picture this is that your annulus A of AB, it so to speak runs from height log A to height log B. And in between, we have this point at height R, or rather at height log R. And we've written log R as P times log A plus 1 minus P times log B. So that means that if we were to regard the whole height as being equal to 1, then the height of this circle, the circle of radius log R, which I've drawn in red over here, it's P of the way up. This distance is P. Now, what's the obvious harmonic function that's 0 down here and is 1 up here? It's just the height in this picture. And so since we're P of the way up, the harmonic measure of B should be P. So I think I've reversed things over here. Let's see, yes. And this shouldn't be 1 over P, this should be 1 minus P. So if Z is, oh no, this is right. So if it's A to the P, then P is large, right? And right. So if it's close to A, then the power of A is close to 1. Sorry, I think I've drawn this picture wrong. So this is right. So this is if we're distance. Right, this distance here is, if this vertical distance is 1, then the distance from the top down to where we are is P. Okay, so the point is that the harmonic function phi of Z, which is log of the absolute value of Z divided by A, is itself divided by the log of B over A. This is equal to 1 on B, and it's equal to 0 on A. Okay, so this is harmonic because the logarithm is harmonic. I've normalized it so that when this is meant to be inside the logarithm, so that when Z has modulus A, you're on the bottom boundary of the cylinder, and this is equal to 0. When you're on the top, you get B over A, and we've divided by that constant on the bottom. And so the value of this function at a particular radius R, phi at Z, where the absolute value of Z is R, which is A to the P plus times B to the 1 minus P, this is equal to, so we get the log of A to the P, B to the 1 minus P over A, all divided by the log of B over A. And this is equal to, let's see here. So this is, let me write this as P log A plus 1 minus P log B divided by a minus log A. Sorry, calculation is running out of control. Minus log A, all divided by log B minus log A. Okay, so now I want to let's see here. I want to divide through by, I'm sorry, I'm just botching this, this computation. Sorry, this is p minus 1 log A plus 1 minus p log B over b minus a. So this is just 1 minus p times log b minus log a divided by log b minus log a. So the upshot is this is 1 minus p, and that's the harmonic measure of the interval b. So indeed, this function shows that the harmonic measure of the top at this circle, its harmonic measure is 1 minus p, and the harmonic measure of the inside is p. And so what we just proved, we apply this bound, and we get indeed that m of r is less than or equal to m of a to the p, m of b to the 1 minus p. Okay, so the upshot is that we know exactly what the harmonic measure is of the inner and outer boundaries of an annulus, even though we don't have a simple formula for harmonic measure on the boundary of an annulus. And by combining that with this basic estimate, we get Hadamard's three-circle theorem. Okay. So next I want to use harmonic measure to prove a more conceptual theorem, and then I want to finish the discussion with an example. So before I do that, let me quickly review some easy cases where we know exactly what harmonic measure is. So the first case we discussed was an arc on the boundary of the unit disk. And here, omega of z delta A is equal to just the length of A divided by 2 pi. It's the portion of the disk that's occupied by this arc. And the second case, which one should know by heart, is that if you have a point in the upper half plane and you have an interval a to b along the real axis, then to figure out the harmonic measure, you just have to draw this triangle and measure the angle alpha at the point z. And then the harmonic measure of z in the upper half plane of A should be equal to, this time, it's the angle alpha divided by pi rather than 2 pi. Now, these two things are not unrelated. You see here, the length of the curve A is the same as this angle beta. The visual angle of A is seen from the origin. So here I could have written that angle beta divided by 2 pi. And here I've written a different angle and I've divided by pi. But this situation and this situation are the same because there's a conformal isomorphism between the unit disk and the upper half plane. So they have to give the same answer. So in other words, in this situation, rather than considering the Euclidean geodesics from z to the endpoints of the interval, we could consider the hyperbolic geodesics. That's in fact the meaning of the statement here, is if we want to compute at any point what the angle is, what the harmonic measure is of A, we draw the hyperbolic geodesics from its endpoint, and then we measure the angle beta at that particular point. So in particular, if we draw the hyperbolic geodesic from Z to B, and we do the same thing from Z to A, then we will get a bigger angle at Z, and that angle should be exactly twice alpha, so that it compensates for the 2 pi on the bottom here. So let me just explain why that's true. the reason that's true is that this hyperbolic geodesic makes a 90-degree angle here. This line is a secant. And so this angle here is, if we compare the angle of, sorry, what I want to say is that what it boils down to showing is that if we have a single point X and we draw this angle alpha here, then if we also draw the hyperbolic geodesic connecting X to the same point P here, then this angle is the same as this angle. And the reason this angle here is the same as alpha is that this angle is the same as this angle. Now, what about these two angles? Well, these are complements of one another because they sum to 90 degrees. So this angle here is the complement of this angle, but alpha is also the complement of this angle because in a right triangle, two opposite angles are complementary to one another. And so when you draw the hyperbolic geodesic, you get an angle that's twice as big here as if you had drawn the Euclidean geodesic. And that explains why these two formulas are compatible. Okay, so those are two examples that we should have firmly in mind. And in particular, we understand very well what the harmonic measure is of, say, the negative real axis. The harmonic measure of the negative real axis, as seen from a point Z, is just this angle here. And now the endpoint of the positive real axis is very far away. But what we get is this angle is, of course, the same as this angle. So in the upper half plane, the harmonic measure of the negative real axis is nothing more than the argument of Z divided by pi. Okay, so let's use this calculation in the upper half plane to prove a theorem. Another basic theorem in complex analysis having to do with what are called asymptotic values. So the setting is the following. Suppose we have a function h, f mapping h into the complex numbers. Let's say it's bounded, analytic, of course. And suppose we have a path, gamma, mapping 0, infinity, into the upper half plane. Let's say proper, that means that the absolute value of gamma goes to infinity. Okay, so the picture is this. And let's say it starts at the origin, just for concreteness. So we have some path gamma going off to infinity. Here's gamma of t. And we say that A in C is an asymptotic value of f if there exists a gamma such that f of gamma t tends to A as t goes to infinity. Okay, so if there's some path which goes to infinity such that the value of f converges along that path to a constant A, then we say that this is an asymptotic or limiting value or a possible assignment of the value of f at infinity. Now, something that you might worry about is whether or not f can have many different values at infinity. Maybe if we chose a different path, going in a different direction, you would get a different asymptotic value. Also, there's an obvious path going to infinity, which is just to go straight up. And if you go straight up, that would be nice if this converges. What if this path converges? That imply that you'll get convergence on this path. Or what if you take paths that lie in a cone? Will these all give the same limiting value? So if the limit as r goes to infinity of f of rz is equal to, let me call it capital A, whenever, say, epsilon is less than, well, whenever, I guess I can just say for all z, for all z in the upper half plane, we say f has a radial limit. Okay, so if you choose these paths and you get convergence, then we're happy and we call those the radial limit of A. So the main theorem is that for bounded functions, if you have an asymptotic limit, then you have a radial limit. So if you can find a limiting value for your function along some terribly behaved path, it automatically has a limiting value along these well-behaved paths. And as a corollary, it only has one limiting value because it can only have one limiting value, one radial limit. So that's the theorem that I want to discuss and explain how harmonic measure enters the proof. So the theorem is if f has A as an asymptotic value, and f is bounded. This is critical. If you were to allow unbounded functions like wild exponentials, e to the z, all hell would break loose, but we're assuming that f is bounded. Then A is also the radial limit value of f. Value of f at infinity. And as a corollary is f has at most one asymptotic value. Okay. So I bring up this theorem primarily as a way of showing how harmonic measure helps in understanding general analytic functions, and also how one applies the monotonicity principle. So for the proof, I mostly want to indicate the ideas because there's some technicalities in the proof, but they're just distracting from the main point. So for the proof, let's first, we can normalize f. That is, multiply it by a constant and add a constant. So the asymptotic value A, which is the limit of f along gamma of t, is just equal to 0. So f is converging to 0 on some path. And we can also normalize so the absolute value of f is less than or equal to 1. Okay, so now everything comes down to a picture. So let me draw a picture that I think is fairly persuasive. So here's this path gamma going to infinity, and eventually f is small on this path. Well, let's assume that f is less than or equal to epsilon here. Why are we allowed to do that? Well, eventually f is less than or equal to epsilon, unless less than epsilon. So let's just translate the plane upward and restart our discussion after the point when f is pretty small along this path. And now this path divides the plane into two pieces. And so suppose we pick a point z over here. Now the value, there's a region here, omega, which lies between this path and the positive real axis. And what we want to show is that f is small at z. However, we want z to be going to infinity radially. So z is confined to some line that makes a definite angle here with the real axis. So we're interested in Z, where our Z is also bounded from below. Say it's greater than delta, greater than 0. So it's going to infinity along a radial line. Okay, now what can we say about the absolute value of f at Z? Well, here on the real axis, the absolute value of f is less than or equal to 1. It's less than or equal to 1 everywhere. Here, it's less than or equal to epsilon. So what we see is that to control the value of f at Z, all we have to do is control the harmonic measure of this part of the boundary of omega. We have one piece here, which I'll call B, which is the positive real axis, and then another piece here, which is this wild, possibly hard to control path. And what we want to show is that this part of the boundary has a substantial influence on the value of f at this point. Okay, so if P is equal to the harmonic measure at Z through omega of this boundary part A, let me just call this gamma, then we get the absolute value of f of Z is less than or equal to the bound we have here, which is 1 to the 1 minus P, times the bound we have on this path, which is epsilon to the P. So as long as we can show that P is reasonably large, the fact that f is small here will force it to be small here. And that will mean that convergence along this path to 0 will imply convergence along this path to 0. That's the idea. And now the problem is, we don't know what the harmonic measure is of A. Okay, so here's the bold idea. Think of this region between gamma and the positive real axis as being obtained from the upper half plane by invading it with this huge looking set A, which includes everything between the negative real axis and the path gamma. So let's stop thinking of A as gamma. Actually, let's just call that gamma and let's call this A. Okay, so this harmonic measure is the same as the harmonic measure at Z through the upper half plane of A. So remember, we adopted this convention that you're allowed to talk about harmonic measure even of a set that invades the region. And we want to show that this harmonic measure is big. Well, making A smaller always makes the harmonic measure smaller. That's the monotonicity principle. So let's shrink this domain A all the way down until it just becomes the negative real axis. So certainly the effect of gamma on Z is less than the effect of the negative real axis on Z. So this is greater than omega of Z, H, and the negative real axis. But we just computed what the harmonic measure is of the negative real axis. This is nothing more than the argument of Z divided by pi. And here's where the radial limit business comes in. We're not allowing Z to get very close to the real axis. It has to go to infinity along a radial line. So its argument is bounded below. So this is greater than or equal to delta over pi. So that says that the absolute value of f of Z, well, not less than epsilon, it's less than or equal to epsilon to the delta over pi. And this value of delta is independent of Z. So as Z moves farther and farther along, and the value along gamma gets smaller and smaller, the value of f at Z also goes to 0. And that shows that the fact that f is going to 0 on this arc forces the value of f to also go to 0 along this radial line. Now you might say, oh, but what happens, what if we were to go along a radial line like this? But exactly the same argument applies now with Z over here in a new domain, omega prime, and then gamma separates this Z from the positive real axis. And this angle here, delta prime, is also bounded below. So exactly the same argument shows that the influence of gamma on this Z is bounded below by the influence of the positive real axis on this point Z, and that in turn is controlled by the lower bound on its angle delta prime. Okay, so this is just a nice instance where the harmonic measure and majorization can be applied, where you see a region that you really have no control over. You want to estimate harmonic measure anyway, and you can very easily do it by just reducing to the upper half plane. Okay, so this theorem, by the way, has some very nice applications for the Riemann mapping. It tells you that if you have a Riemann map and you have a point on the boundary of your region which is accessible by some path, then in fact there is a radial limit at that point for the Riemann mapping as well. That's made precise in the notes. But I really think the issue with harmonic measure is a lot of it is in gaining intuition for it. And when we do probability theory, we'll have a very strong method for gaining this intuition. But I just want to conclude by giving some examples to help you understand how harmonic measure behaves. So we're going to do two examples. The first example, we already understand very well. We're going to take the A to be the interval from -1 to 1 in the upper half plane. So omega will be h. And then we're going to take a point z. It's x plus iy. And what I want to understand is, how does the harmonic measure behave as z goes to infinity? So how does the harmonic measure of zh behave as z goes to infinity? And then the second example is going to be one of our favorite regions. It's the half strip of height pi. I've called this S plus in the past. It's a half infinite rectangle. And there's a very natural question here as well. Suppose we take the midline of this rectangle and pick a point here on it, z, which would be x plus pi I over 2. And we can again ask, how does omega of z s plus a behave? In this time as x goes to infinity. Here we might say as y goes to infinity. Maybe we're interested in just going up the y-axis. Okay, so let's try to answer these questions. So for the first, things are pretty easy. We know exactly what the value of the harmonic measure is. It's this angle alpha. In fact, in the first case, omega of z is equal to exactly the argument of z minus this point, z minus 1, minus the argument of z plus 1 divided by 2 pi, divided by pi. Now, what does this quantity look like? This, what I've written down is, it looks very much like the derivative of the function argument, right? We've taken the function argument and we've evaluated it at 2 points that differ by 1. So this is approximately the derivative with respect to x. See, we've changed the x value of z by -1 here and by +1 here. It's approximately the derivative of just the argument of z with respect to x, except it's with a minus sign, because I did -1 first and then +1, and it's with a 2 multiplied by 2, because the difference between these two endpoints is 2. So it's approximately, this quantity on top is approximately -2, the derivative of the argument, and on the bottom, we have pi. And now this is something we can evaluate directly. if you take z and you move it over a little bit, how fast does its argument change? Well, let's do the special case where z is on the y-axis. So if z is on the y-axis, on the imaginary axis, then when you move it over by a certain distance x, its argument is the length of this arc divided by the radius of the corresponding circle, which is y. So, so this is approximately equal to, and it's negative, by the way. The angle is decreasing as we move x to the one side, and it's approximately equal to the 1 over y. So it gets, so what we see is that as you move along the imaginary axis, the visual angle of A goes to 0, but it goes to 0 at a polynomial rate. It's 1 over y to the power 1. So harmonic measure decreases polynomially, or by a power law. In other words, it's something like 1 over y to some power. Okay, now the situation of a strip is similar to the situation of the upper half plane. In fact, one is contained in the other. But how do you get from the strip, from the upper half plane out of the strip out of the upper half plane? What you'd have to do is make your domain smaller. Now, does making the domain smaller make the harmonic measure go up or down? Down. Bigger, making anything bigger makes it go up, making anything smaller makes it go down. So the harmonic measure here is going to go to 0 faster than it would in the upper half plane. And in fact, in case B, we can easily see that omega of, let's say, x plus the midpoint, pi over 2, pi I over 2, goes to 0 exponentially fast as x goes to infinity. Okay, now one way to prove this would just be to say, let's go ahead and calculate what the harmonic measure is. And we can do that because we happen to know a beautiful conformal map that sends this region exactly to this region. Does anybody remember what that map is?
Kosh, maybe?
Yeah, exactly. It's Kosh. It's Kosh. So Kosh sends this edge, you know, Kosh of 0 is 1, and it's real on the real axis. So Kosh sends this edge to this edge here from 1 to infinity. And then Kosh, the Kosh of I theta, this is an identity everyone should know, it's just the cosine of theta. So as you go along this edge, this interval here is mapped to this interval here just by the cosine. And then when you go along this, Kosh takes over again, but now it's multiplied by a minus sign. And so this edge gets mapped to this edge gets mapped here, and the other edge gets mapped to the part of the real axis greater than or equal to 1. So we could take the answer that we have here, pull it back by Kosh, and get it and just compute. But there's a much nicer way to think about this example, which is not 100% accurate, but which allows you to understand why this goes to 0 exponentially fast. So here's the idea. Let's let m of x be the soup of the harmonic measure in z s plus of A over the real part of z is equal to x. So we just draw a vertical line somewhere here in our S plus at some point x. And we have a function that's equal to 1 here, and it's 0 here. And then we look at how big it can be on this line x. Now we know it can't get up to 1, by the maximum principle. It can't achieve its maximum in the interior of the region. So this maximum along x is something less than 1. But now let's suppose we now want to understand x plus x prime. And we want to look at the soup over this region here. So we move an additional distance of x prime. Now the beautiful fact is that this half-infinite rectangle that starts at x is isomorphic to our original rectangle. And so we can use our understanding of harmonic measure on the original rectangle to bound the value of the harmonic extension at x prime. But when we go to this smaller rectangle, we have a function that's not equal to 1 here. This function is less than or equal to m of x on the boundary, instead of being less than or equal to 1. And so it's bound on this line is not m of x prime, it's m of x prime times m of x. It gets smaller because we have a better bound on the value of the function at the edge of the half-infinite rectangle. So by the maximum principle, what we find is that m of x plus x prime is less than or equal to m of x times m of x prime. And it's this kind of reasoning that is used to great effect in the study of harmonic measure. When you don't really understand what the function is, what's ideal is if you can find some sort of property that it enjoys. And here, it's almost like a group homomorphism to the multiplicative real numbers. It's just sort of submultiplicative instead of multiplicative. In any case, what we can conclude from this is that if we take m of n times x, whatever x is, the harmonic measure there is less than or equal to m of x to the n. And just by iterating this inequality n times, and for any particular value of x, this number is less than or equal to 1. So for example, m of 1 is equal to some number lambda less than 1, and we conclude that m of n is less than or equal to lambda to the n, and of course this goes to 0 exponentially fast. Okay, so when you're floating around in the upper half plane at distance d from A, the visual area of A looks roughly like 1 over d. But when you're confined to this strip, it's very hard to see all the way to the end, and the visual angle of this interval at the end goes to 0 exponentially fast. So I have 1 minute left, and let me use it to just draw your attention to a figure on the webpage for the course, if I can pull that up. Hang on a sec. Which was meant to illustrate exactly this example. Here we go. Okay, let me see if I can share this. Okay, so this is our, you have to imagine that the strip goes off infinitely, an infinite distance to the right. What's drawn in the upper figure are the level sets of harmonic measure. It is in fact decreasing exponentially fast, but that might be hard to glean from this picture. But the bottom picture is more realistic. What it's showing is what the geodesic rays look like when you're standing at a point in this region and you're trying to look at the endpoints of A. And what you see is that when you're close to A occupies almost 180 degrees in your visual sphere. But as you get farther and farther away, these visual rays get rapidly nearly tangent to the horizontal line. And as a consequence, A looks exponentially small in your hyperbolic vision on this strip. Okay, so next time, a few more words on harmonic measure, and then we're going to go on to capacity. There is a section on curvature in the notes that I hope you'll look at. It's not very long, But I think in the interest of time, I'm going to go on to capacity and extremal length, and then that will end our section on conformal invariance, and we'll start on the probabilistic perspective on these kinds of issues. Okay, so as usual, I'll hang around a bit and I'll stop the recording.